we have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
The Kepler mission is a huge step forward in answering the question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the habitable zone.
The habitable zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and the planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours, and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures, but the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a Sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth-trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the Sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
Kepler will be looking in a region of the sky that you'll see almost every night in the summertime.
The field of view is kind of nestled underneath the wing of Cygnus the Swan, between Cygnus and Lyra. Now, in that area of sky, there are something like 6.5 million stars. Why do we need so many?
Because of the way Kepler looks for planets, we have to have planetary systems that are lined up so that the planet actually passes between the star and Kepler telescope in its orbit.
The probability of that happening if you just throw stars randomly down in our galaxy is something like 1 to 10%. It's small. So of those 6.5 million scattered over that 100 square degrees, only maybe 200,000 are interesting to us.
We select the 170,000 or so that are most suitable to look at for planets with the Kepler telescope. Finally, we expect to end up with somewhere between a few hundred and a few thousand signals that are really planets around the stars that we're looking at.
Well, this is the first time that photometry, the measurement of the brightness of stars, will ever be done at this level of precision. And it will be done simultaneously on more than 100,000 stars continuously over a period of years.
We're somewhat like pioneers, very much like the explorers that were looking for new lands to settle. And that's how I see what we're doing. We're looking in this region of our galaxy for other habitable worlds.
I think people everywhere want to know whether with all the stars out there, do they have planets that are Earth-size? Are Earths frequent or are they rare? And this gives us that answer. It's the next step in mankind's exploration of the galaxy.
There's two extreme answers that Kepler might give us. It might tell us that there's an Earth-like planet practically around every star we look at. Imagine the possibilities for life in the galaxy or life in the universe.
If, on the other hand, we found out that Earth was very special and that the typical star, like the Sun, is not hosting planets like the Earth, I think that would be a real surprise as well and would really make us reconsider the special nature of Earth.
We are now finally at the point where our technology allows us to build a machine that can make the observations to scientifically answer this question.
How many stars like the Sun did develop planets around them like the Earth? I think that's such an important question to everyone and so interesting that we really have to do it, and it's a once-in-a-lifetime opportunity right now.